it's really helpful to be able to print things out with more control, with more refinement. So what we're going to do is use the fprintf command. Okay? So this is the same in any other language as just the printf command. That's the key thing. It has C roots, the C programming language. How many people here have never used a printf command in their lives before? Okay, a good chunk of. How many people have used the printf command in their lives? Like, okay, weird. Good job. All right, so if you have seen it, bear with me. If you haven't seen it, it's a little counterintuitive at first, but if you get the idea of it, it works out not too badly. So there's a script we provided for you, W22. So I'm just going to open that up here. W22. And the idea is just to do some sample output. So I'm going to comment all this stuff down here, Control R, Command R, and I'm going to run everything else. And the idea is, if you have a value you want to print, say in this case A, which is 5, we can print it in a bunch of different ways. I'm just going to do a quick CLC here. Oh, there's stuff further down. Sorry, I missed the bottom part. Comment that out. All right. So when we look at the print statements, the % sign gets a little overloaded here, so bear with me. Inside this line, basically you can see, hey, I printed A equals 5 is the first thing. That comes from that printf in single quotes A equals %D. You can also use, I think, if you want, I for integer. I grew up with D for some reason, so that's what I always use. Yeah, that works too. So if you want the mnemonic, I works fine for integers. F is for a fixed decimal place, and E is for exponential notation or scientific notation. And you can see the different formats. The D just prints out, hey, it's an integer. I'll print out an integer. The F prints out a certain number of fixed decimal points afterwards, and the last one prints out exponential notation. So it's 5 times 10 to the 0, or just 5. So what you do is you put in a little place marker saying, a number shall be inserted here in your quotes, and then after the quote, you put in what you want, the variable, the name of the variable you want printed in there. So we're going to say, I'm going to print an integer. What integer? I don't know till I get to the end, and the integer is going to be whatever's in A. Likewise, for the next 3, it's all just print something in here with a certain format, and A is going to tell me what number I'm actually going to print when time comes. Okay. Let me pause there before we get to the more exotic versions of the fixed format. Questions or comments? Okay. All right. That's usually pretty crude. So often we're going to refine that further by adding some extra precision here, extra control. All right. First thing, we're going to make b equal pi. So to the limits of what MATLAB knows about pi, which is 3.141659, blah, 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 we're going to try to print that number, which has a lot of digits to it, a lot of decimal digits. If we try to print it as an integer, it actually just gives up on us and says, this is not an integer, go away. It's probably not what you want. But it does something, at least print something. That's the first one. The second one is the default. So print fixed decimals, and it defaults to just showing you 6 digits after the decimal. Then you can say, hey, I don't want 6 digits, I would like 8 digits. So you just put the 0.8 here. So point to say, after the decimal, 8, tell you how many digits. Then you can do some other fun stuff and say, how many digits in total do you want? And you'll see that this one here is spaced out a little bit. It actually has 15 digits all the way from start to finish. But because there's only 1 in front and 8 afterwards, it gives a big gap there. And you can refine that a little bit. The 12/8 sort of moves it around a bit. So you get a fair amount of control here, which sometimes is really important just for being able to process your output in a sensible way and not going, wait, where did all my decimal points go? Line them up for me. This is a nice way to have it work. All right. Questions or comments about that formatting layer? That extra ingredient to the point F. Yeah?
What's the default of the
%F is 6 digits. 6 digits after the decimal. And it'll do however many it needs in front of the decimal. Yeah?
What's the slash n comma for?
Oh, what's the slash n comma? Yes. So if I don't put the slash n here, how many people have seen the slash n before in their lives? Show your hands. Again, the same people. All right, excellent. So if I take those out, let me show you what happens. I'm going to run it again. I get this. So what do you think the slash n does? New line, exactly. It takes you down one line. So honestly, I didn't even think about it there because it's just automatic right now. /n at the end of your print statement. It's just, I did not even think about it. So if you want new lines, you just factor that into your statements. So the /n as a pair, it has to be the combination. The / and the n is the special symbol. Go to the next line. The quote comma is more MATLAB. So the idea is you've got a string, everything that starts and ends the quote. That's one input to your function, comma, the next input b. So it's a string, quote, quote, comma, what variable you want to print. Did that make sense? Awesome. OK. So last but not least, because MATLAB has matrices, because it's the matrix laboratory, we can print out a vector pretty easily. So here we're going to show a little bit of sort of boilerplate that you use for loops and cycling over vectors. I create a vector x that is 1, 1.52. So that's the colon notation. Then I said let v be those values squared. That's fine. So I have 3 numbers in v. And you can print it this way. You can actually list them off. So let me just cut and paste that down. CLC. We can say, please print. Again, the only thing that matters in terms of the numbers is the % sign, whatever. So print to 4 digits, some number. 4 digits, some number, 4 digits, some number. And then we give it v, which happens to have exactly 3 numbers in it. And it's happy. It'll go, the first number gets printed after v1, the second after v2, the third after v3. So that's one way to do print statements of multiple values. That can be a bit cumbersome, though. So another way to do it, because we had to list it off, right? Another way to do it is to do it inside a loop. So we're going to have a loop that starts it, that is counted by I. I is going to go 1, 2, well, what's the length of v? Length, remember, is the number of elements. So there's 3 elements in v, so it's going to go 1, 2, 3 for I. And then our print statement is going to take advantage of both of those numbers. So we can print with multiple values. There's 1% thing here that says print an integer. I'll change it to an I here to make it consistent. And then there's another print statement with an f, so that's the digits. And notice the order. I'm going to want you to print first the I, the counter, 1, 2, 3. And then after that, I'd like you to print the ith element of v. And that gives us the nice output here. Function F9. There we go. So that's a nice way to do it. It automates the counting and the v1, v2 stuff. If there had been 10 elements of v, it would have printed 10 elements of this, and it would have numbered them for me. It would be really easy to interpret after the fact. Very easy to parse that. So 2 variations there. Depending on how many elements you have, you either use a simple print statement if it's 1 or 2 or 3 maybe. Anything past that, I'd usually break out into the loops. OK. Now what we're going to do is apply that to our current problem, which is working on the forces. Because again, if I run this force thing, I get this sort of ungainly list of stuff. And I would like to actually have it labeled nicely and printed out pretty like. So what we're going to do is actually borrow that code that we had in the last example. We're going to copy it over. So we're calculating the forces. I'll put a semicolon on the end because I don't really want to see the forces yet. I want to see them when they're pretty, not when they're just calculated. And a couple changes. F is our vector. So I'm just going to change all the F's to, all the V's to F's there. Okay. So now what we have is a separation of the calculation, which is the F equals A slash B. That calculates the forces. And then we're going to go and print them nicely with this last loop here. So I'm going to clear the screen here, run that, and okay, that's better, a little bit better. We can actually see the thousands, we can see the zeros. It's not great, though. What would make this nicer? What would make this nicer? Any suggestions? You're all ecstatic with it the way it is. Yeah, what? Units. Oh, yeah. We could. These are. What are the units of these forces? If they're forces, they're probably all the other. Really? What? Newtons. Let's go for newtons. Right. So inside the quote, this is just a part of the text. We can add a newtons at the end there, just before the slash little n, and that'll make it look like newtons. Fantastic. Anything else that would make it easier to parse? Any other suggestions? Yeah. Put a 5 or 6. All right. Why would you want to do that?
So not the negative sign of b
So things are lined up a bit better. Yeah, I mean, you got these things, the decimal points are not lined up. So what we can do is use one of those earlier examples where we say, let's put a big number in front here. Let's say 10. I'm going to experiment as hey, wow, that was awesome. So it says use 10 digits for every number, and all of a sudden, bang, everything's lined up. You can just look down the left column and see the scale. Everything's fantastic. If you didn't do something as big as 10, if you did something like 6, because that's your first guess, it'll start doing stuff, but not that much. Because the 6 is actually how many digits in total it saves. So you usually put a pretty big number in here. If you put a bigger number, it'll just shift everything to the right. There we go. So that makes it look a lot prettier, honestly. Any other changes anyone would recommend? Those are the big ones for me, but there might be others. Yeah?
I don't know how this can be done, but like change the negative sign to like an up, down direction.
Change the negative signs to an up or down direction, or say tension or compression, right? So that would not be just a simple print statement thing. What you'd have to do is a little if-then part of this. So you could say, in your loop, if the force is negative, then print the word compression or something like that. So that'd be a little more involved than we necessarily want today, but it's very straightforward. It just takes another couple lines of code. Okay. My only other thought, honest to God, is just being with an engineering hat on. Do you think we care about 4 digits of accuracy to the force, the newtons? 0.0001 newtons? Probably not so much. So beware of over-specifying your output a little bit here. Honestly, we probably might not even need more than 0 digits. Let's try 0 digits. And like 10 of those. That's really the scale of the numbers that are going to be of any interest to you. Basically thousands, 1400s, and take it from there. All right. So that's nice because it also makes it really easy to read. You can hand this to someone else, give them the diagram, and they can actually put those forces on before you had to do counting. This is just a little nicer to work with. Any difficulties or questions coming out of people trying this on their own? Yeah?
So if you take that off, like it doesn't round or anything, right? It just cuts off the end.
When you put the 0.0, no, it actually rounds. It actually does round, I think. Let's put 0.1 and just make sure. But my recollection is that it rounds things. That's not really helpful because it could be cutting them off. Let's go for 2. It's still not rounding because we can't tell. There we go. So this last one here is 227. When we go back to 2 digits, it's 23. So it's rounding. So it's doing what you'd hope for as an engineer. Yeah?
When I run the code, I get a positive 0 for F3. You get a negative 0.
Ah, yes. The old negative 0, positive 0 problem. So F3 and F4 are a little bit dodgy here. All right? Because what's minus 0 versus positive 0 to most of us? There's 0. Okay? What happens here is, if we focus in on F3, here's what F3 is to me. It is not 0, actually. It's negative 1 times 10 to the negative 13, way down there in the far end of things. That's what we'd call round-off error. That's something that's so small, first of all, we don't care because it's 10 to the minus 13. And numerically, it's not that interesting. But the weird thing is, depending on your computer and the particular version of the code you're running and the Mac versus PC chips, you might get positive 1 point blah, blah, blah times 10 to the 13, and that's OK. This is the kind of round-off error that creeps into numerical calculations as long as it's not on the same scale as the numbers you're interested in. We just sort of say, oh, that's really annoying that it says negative 0, whereas yours says positive 0, but as long as it's small enough that we don't care, we just let it go. We will talk a bit more about numerical accuracy a little later on in the course. It's not a huge theme of this course because most of the stuff we do is pretty safe, but it is something to be aware of, that 0 isn't exactly 0 in MATLAB, and very rarely is exactly 0. It's very, very close to 0. What if it does just equal 0? That's great. Honestly, if you found that it equals 0, that we'd be ecstatic, but it's not generally going to happen. When you solve linear equations like this, usually some small round-off comes in. And you'll see that different variation between computers, between versions. It's just, so don't expect things to be identical, but you would like those first 4 digits, for example, to be the same between your computer and your neighbor's. If those aren't the same, then we have a real problem. Okay. All right. Last little stretch of this. We did all that. Fantastic. There's a little note here about how to index. So I was using some syntax there I didn't actually introduce before I did it. but I think a lot of you have seen this before. Let me just confirm. We have a vector called f, and when I said f bracket 3, I got the third thing back out of f. How many people have never seen that idea before in their lives? Like 3 of you. Okay, so that's it. That is the idea right there. I'm going to add one little layer of sophistication to that because we're going to need it later on. The idea is, sorry, let me type that out again. If my full vector f is all these numbers, I can put, if it's a vector, I can just put one number in because it's just, doesn't matter whether it's row or column. I'm just going to get the first element of f. We're going to need that a lot. And it's exactly, if you flip back through, what the first element of f was. So if we want to tease out individual elements, that's how we do it. If we have a matrix, though, we're going to need a little more specification. So let me just do this quick run here. I think it's here. Yeah. So if I make a matrix, A is 1, 2, 3, 4. And I want to grab this element down here. I need to specify the column and the row. Which do I specify first, row or column? Row. It's always row, column, row, column. So I want the second row, first column. So if I say, what is A in the second row, first column, I'm going to get a 3 back. What's A in the second row, second column? It better be a 4. Right. So if there are really two dimensions, you'll need to specify 2 dimensions. If it's just a vector, either a row or column, it'll actually let you get away with just one value, which is often easier to think about.